So, welcome to the topic of defected ground plane structures microstrip antenna. Now, as the name suggests, defected ground plane structures means what? We are incorporating modifications in the ground plane in the form of slots or shape of the ground plane, and those modifications are aimed at realizing particular response from the patch. So it can be a compact antenna design, it can be a broadband antenna design, it can be a circular polarized design, or that defected structures can be used to realize enhancement in the antenna gain. So various possibilities are there. Now first we should understand why we are going to consider the defects in the ground plane to achieve this. Remember, a microstrip antenna in simplest form consists of the radiating patch backed by the ground plane. Now if you look at the side view of the microstrip antenna, it looks like this. Okay, you have the patch, then there is a coaxial connector which is feeding the patch, and then there is a ground plane. Remember, ground plane dimension is more than that of the patch dimension. Okay, we define the resonant modes for the patch. Similarly, the resonant modes can be defined for the ground plane as well. Okay, because there is no such constraint in the design of microstrip antenna, although we take it that way, but there is no such constraint that this dimension has to be more than this. There are some designs in the literature which offer certain antenna characteristics where the ground plane dimension is taken lower than the patch dimension. Okay, why? Because how the ground plane dimension is identified? Because the ground of the coaxial cable is soldered over there. So that is definitely identified as a ground. So that dimension can also be lesser than the fed patch dimension. Of course, it offers certain antenna characteristics. Of course, it has a disadvantages also. But you can create some modifications in the ground plane which can realize certain antenna characteristics. Moreover, the ground plane modifications have been exclusively evolved, exclusively understood for realizing a cross-polar radiation reduction. Now we have already learned about what is cross-polar level. In simpler, I'll just summarize that point. If this is your direction of the antenna polarization, and if this is the incident electric field vector, how much the antenna will receive the energy from the incident electric field vector, that defines the cross-polar level. Or rather, what is the susceptibility of your antenna to receive the orthogonal polarization? Ideally speaking, a microstrip antenna operating in fundamental TM10 mode or TM11 mode, they have a very low cross-polar level. How much low? Minus 30 dB down, minus 35 dB down with respect to the copolar level. But in certain applications, even those kind of cross-polar levels are not preferable. They want cross-polar reduction further, maybe 60 dB down. That kind of a cross-polar level reduction is required. What it implies that you do not want even a minus, smallest of the weakest signal that should be picked up by your antenna, because that can be treated as an interfering signal. Okay, because nowadays you have so much sensitive receiver, even the minus 40 dB down signal can be picked up and it can be processed. So you want to brought down that cross-polar level to as low as possible. So in such designs, you require a very low cross-polar level or very high reduction in the cross-polar level. Now, going to the cross-polar level, we have seen that if this is the antenna polarization and if this is the incident level, the cross-polar level depends upon the bidirectional current nature on the patch. We have seen in case of rectangular microstrip antenna, when you excite that antenna in the fundamental TM10 mode, then what will happen? The surface currents are directed along the patch length. The surface currents are directed along the patch length. There is only Jx component present. There is only Jx component present. There is no Jy. So if there is no Jy, the cross-polar radiation coming from that Jy component is zero, ideally speaking. Okay. Plus, there is no radiation coming from the non-radiating edges because it is absolutely getting constant. So with respect to the main dipoles, the magnetic dipoles which accounts for the radiation pattern in TM10 mode. There is no orthogonal radiation which is happening in the rectangular microstrip antenna at 10 mode. But still you get minus 35 dB cross polar level. Then what is the source for that? The source for that comes from the higher order modes. Now how the higher order modes are contributing to the cross polar radiation at the fundamental mode? Let's understand this concept. This is a microstrip antenna. Here we already have said a driven mode and the eigenn modes. I will not excite this microstrip patch with any coaxial cable. So without that, all resonant modes in the cavity are present. Now when I excite this antenna with a coaxial probe, driven modes are there. Now when I am exciting this particular microstrip antenna at 10 mode radiation, for that feed point location, TM02 mode is also excited. And the distribution of that I have shown. This is the field distribution for TM10 mode, and then orthogonal, this is the field distribution for TM02 mode. That is the component, the distribution that will be present at TM02 mode. Now how does it affect at 10 mode? Because you can say, suppose I am designing my rectangular microstrip antenna at 900 MHz, that TM02 mode will appear at 1.5 or 1.6 depending upon what is W/L ratio. But here, remember, this is the resonance plot I have shown. This is the 10 mode appearing at say 900 MHz, and this may appear at somewhere around 1600 MHz also. So how does that particular mode affects the performance at 900? Remember, in a rectangular microstrip antenna cavity, always, since that mode is excited, there exists some kind of a residual contribution at the lower order mode frequency. That mode is not completely bypassed. Maybe 2%, 5% residual contribution of that mode, field contribution of that mode is present. And that residual contribution, what it will do? What is the field distribution of that? It is basically current variation along the vertical direction, 2 half wavelength variation. So naturally, in addition to Jx, you are having a Jy component coming as a residual contribution from the higher order mode. Similarly, you have TM21 mode, even that can get excited for the same feed point location. So multiple higher order mode contribution, their residual mode contribution is coming. You need to reduce, you need to remove that residual mode contribution appearing at the fundamental TM10 mode. And the best way to do that is to go on increasing the separation between the fundamental and the higher order mode. For that, defected ground plane structures are used. This is the basis of cross polar level reduction in the defected ground plane structures. Okay, this is the basis. In fact, using, as I mentioned earlier, defected ground plane structures we have used. I will show you some of those configuration. Like earlier we have seen the U-slot cut design for circular polarized radiation. Even defected ground plane structures using U-slot we have used for circular polarized radiations. How that will I will tell you later. Okay, so this is the funda, because from here all research related to the defected ground plane structures evolved. Later on, the advantages of defected ground plane structures with respect to compact, with respect to wideband, with respect to multiband response, or even the circular polarization are investigated. But the basis started from here. So cross polar reduction is the most important aspect. And remember, for very sensitive receivers, cross polar should be minus 60, minus 70 dB down. And those kind of reductions are only possible if I play with the positioning of all higher order modes, if I isolate my fundamental mode with respect to all higher order modes. So here, my main job is to reduce the residual contribution. For that, I am going to employ the slot. So here, remember, slot around the patch, they are put below the periphery of the patch. Remember, as I said earlier, role of slot in the broadband design, compact design, DGS are different. Similarly over here, if you observe, this is the slot position. Right below the periphery of the patch. They are not present inside the patch, below the patch or on the patch. They are right below the periphery of the patch on the ground plane. Okay, I will show you the pictures of such antennas later, which we have fabricated and tested. So they are placed right below the patch on the ground plane. So here probably you will be cutting that patch slot on the ground plane. What it does, it basically creates the effect on the orthogonal mode frequency, because whenever you have a slot here, this modal current is not affected. Okay, this modal current is not affected because largest dimension of the slot orthogonal to the modal current is minimum. Okay, because this is the only contribution which is there, which is small one, and that slot is not placed in the patch center. So effect on TM10 mode frequency are absent. Okay, so here this slot, when you go on increasing the dimension, it has very minimal effect on 10 mode, but it is going to reduce the effective current path length at 02 mode, because ground plane below the patch at 02 mode is shrinking. So if that happens, effective current length is shrinking on the ground, and that increases the spacing of TM02 mode with respect to 10. So it drives away the TM02 mode frequency with respect to 10 mode frequency. Similarly, and remember, to 21 mode also it has a variation along width. So that mode is also driven away with respect to the fundamental mode frequency. That contribution is reduced. So if this is the copolar and cross-polar level for rectangular microstrip antenna, if this level is minus 30 dB, with this kind of technique you can achieve minus 55 to minus 60 dB down cross-polar level using these defects on the ground plane. Remember, lot of variations are there, lot of configurations have been evolved, lot of combinations of slots have been evolved for reduction in the cross-polar level. Okay, this is one of them. In fact, you can cut a slot like this also. There are so many variations are there. Then even L-shaped kind of a slots have been evolved. So many papers are there in the literature where different configurations have been considered. This is why I am talking with respect to the rectangular patch. Similar study have been done for circular patch geometry. For example, if this is a circular patch, then the slots were put like this. Arc-shaped slots also were put around the ground plane. So this is related to the cross-polar separation. One more technique which has been used for reduction in the cross-polar level is the shorting post. Is basically the shorting post. I will explain that technique first and then I will show you the pictures. See, this is your fundamental mode rectangular microstrip antenna, TM10 mode. Okay, so this is operating in TM10 mode, and then this is your orthogonal 02 mode distribution. Okay, so what we are doing now, I want to suppress 02 mode. What people have done, they have put shorting post. They have shorted these points along the patch boundaries. So when you do that, the 02 mode contribution is suppressed or its frequency is increased. So instead of the slot which is cut on the ground plane, a shorting post is placed around the periphery of the patch, and using that 02 mode frequency is increased in value, or it is cut off, rather it is removed from the structure. So because of that, the cross-polar level reduction is achieved. Similarly, if you refer to the circular patch design, these papers are there. It is for circular patch design, TM21 mode is the source of generation for cross-polar level. So there a cluster of shorting posts have been put for realizing the cross-polar level reductions, because ultimately it suppresses your higher order mode. Remember, the shorting posts are not put over here, neither put over here, because they affect the fundamental mode frequency. I do not want that. The positioning of this shorting post affect only the higher order mode frequency. That's what we are doing. Okay, so this is the basis of cross-polar level reduction. The slots, different forms, different configurations are there, using which you realize the reduction in the cross-polar level. So I'll just show you some of the configurations or pictures related to what the configuration looks like when we are doing this cross-polar reduction. See this. This is the fundamental mode distribution, and these are the slots which are placed below the patch. So when you are putting up slots below the patch, 0 to mode currents are affected, their frequency is increased and you get a reduction in the cross polar level. There is no point in placing the slots inside and below the patch because it has it may affect your 10 mode frequency. So the slots are placed right below and then it causes the reduction in the cross polar level. Okay, so I'll just show you the fabricated antenna. This is the excited in 01 mode and you can see the slots are placed right below. Remember, the positioning of the slot is on the ground plane. It is not affecting your 10, but it is affecting your 02 mode distribution frequency, so that the frequency spacing can be increased, cross polar residual contribution is removed and cross polar are reduced. Okay, so this is the first thing what we do for defected ground plane structure configurations. Another thing which people have widely reported is the compact design. Compact MSA is another wide topic. We have separate lecture series for that, so I will not get into the details of this. Even the compact antennas are realized using the modifications in the ground plane. Now, why compact antennas? Remember, microstrip antenna is a parallel plate structure, two parallel plate structure, patch and a ground plane. So any modifications which are taking place on the ground plane are linked through the fringing fields to the modifications on the patch, because this will interlink. So if I create a defect, like this is a defect created on the ground plane, through the fringing field that defect is linked onto the patch, and those defects create the perturbation in the modal currents on the patch. Thus, any compact technique of slot which is obtained, which is realized for the patch, the same compact technique can be realized for the ground plane also. And we have made a comparative analysis for slot on the ground as well as the slot on the patch. A detailed comparative analysis for different slot configuration. Right now I have just shown the two cases for C shape and H shape. Different, all possible slot cut configurations, bow tie, center slot, two slot, everything has been carried out. And what we have observed, that slot on the ground plane and the slot on the patch provides more or less similar reduction in the frequency. But slot on the ground plane provides a better control of the impedance variation, because when you put a slot on the patch, impedance increases. Okay, those details you can find it in the compact microstrip antenna lectures. So their slot on the ground plane, on the patch increases the impedance variation, whereas slot on the patch, level of impedance variation is not higher, so you are easy to control that. Because why it is required? To obtain the impedance matching for broadband compact response, impedance control is required. Hence, that is much easier to achieve using slot on the ground plane against slot on the patch. So that is the advantage of slot on the ground plane. Reduction wise, frequency reduction wise, more or less it is the same. The only price which you pay over here is slight reduction in the peak antenna gain, because the modifications in the ground plane creates a backlobe radiation. So that is the only thing which you pay, maybe 2 dB down peak gain value you obtain for the slot on the ground plane against the slot on the patch. So that is the only price what you pay. So first technique which was there for defective ground plane structures was a cross polar reduction. It all started from there. Then this compact thing came. Now similarly, wideband antenna designs have evolved. So many iterations are there, so many different configurations are there. I have just shown you one. In fact, detailed analysis of this kind of structure can be done. Like you will see, this is the M-shaped patch, and below that you have a M-shaped slot ground plane. Similarly, there is a paper in the literature, a U-shaped slot patch is there, U-shaped patch is there. Below that, inverted U-shaped ground plane is there. A U-shaped slot ground plane is there. But why these kind of modifications lead to the wideband response? Those kind of things are not discussed and reported. Their modal analysis. What I mean by that, whenever you do any modifications in the patch, which are the resonant modes which are contributing to such wideband response needs to be discussed. Because when you analyze that, then the gain variation can be assessed. Remember, gain variation, antenna gain has to be measured in one particular direction. A maximum gain in all sorts of direction is not important from the user point of view. So gain variation with respect to the direction has to be assessed. So when you design any antenna, the aperture distribution changes. So likewise, the gain variation is bound to change. So assessment, clear assessment of the resonant modes while realizing any particular response with view of the gain variation is an important parameter, and those details unfortunately not available. It is an open topic of research. One can really analyze this and can come up with the original explanation about why this kind of antenna. Definitely antenna idea is novel, because the kind of bandwidth what you get is really a ultra wideband kind of a configuration, because the bandwidth is from almost 2 gigahertz around 9 gigahertz. So it is ultra wideband design, more than 100% bandwidth. So that is a beautiful configuration. But why that broadband response is obtained? Which are the modes which are contributing to this wideband response? That needs to be assessed. So again, this is a wide open topic. One can really look up into this for coming up with the original explanation for understanding of this wideband response. Okay, so you will see similar many such papers. So modifications in the patch, parasitic patches are there on the ground plane. Many different configurations are there, but unfortunately in those papers we do not find why that is done. Remember, whenever you do any modifications in the geometry, you should have an answer why and what impact it will have on the aperture distribution, because everything is linked. That why answer should be there with us. Then only you put the things for simulation. Then you will expect what kind of a result is going to be. Then you have proper justification for the results obtained. Okay, so such beautiful configuration should be analyzed, and you can actually come up with some kind of a design methodology also for this response. Because for example, I want to cover the entire UHF band. I want to cover the entire UHF band 300 to 3000 megahertz. This antenna is useful. So let's come up with that design methodology to realize that configuration at any given frequency. Okay. So this is the case of wideband antenna. This is the case of circular polarized U-slot cut defected ground plane structures, but these are fractal geometries. Now what I mean by fractal means iterations. First order, second order, third order iterations are created. Remember, this is a first order iteration, 0th order iteration of the U-slot. Then this is the first order iteration of the U-slot, second order iteration, third order iterations. Okay, these are called as the fractal variations. Fractal variation means iterations of the fundamental slot structure is repeated n order times. So like this is the first order U-slot, then this is the second order U-slot created, and the third order. Now what it does the similar thing to what you have seen in the U-slot cut design. Okay, what it does a similar thing to what you have seen in the U-slot cut design. Now let's understand what exactly it does. In fact, it is also similar V-slot cut configuration also can be tried with a slot on the ground plane rather the slot on the patch, and it may give me a better AR bandwidth, axial ratio bandwidth. So that kind of configuration can be explored for the slot on the ground plane against the slot on the patch. So here what you can do is, when you have a radiating patch and when you create this slot below the patch, I should say, not over here. This is the slot below the patch. Similar effect it does. Similar effect it does. It creates, this is the feed point location, it creates two diagonal modes. Because when you have a slot like this below the patch, definitely the diagonal distances are different along the two diagonal lengths below the patch, and that has an effect on the radiating patch. So that creation of two unequal diagonal lengths relates to the creation of two diagonal modes, what you have seen in the U-slot cut antenna. Again I repeat, when you are cutting this slot, remember this is creating unequal diagonal length along the patch two diagonal sections. So that has a creation of the two orthogonal modes on the U-slot cut defected ground plane patch, and that leads to a CP response. In fact, this we have done a rigorous study with respect to the first order, second order and third order iterations of the U-slot in circular patch as well as in the rectangular patch, and what we found that first order on a thinner substrate gives me optimum response. Almost 3 to 4% of axial ratio bandwidth is obtained. Okay, similar variations can be tried with respect to the Y shape or V-slot variations, because V-slot iterations can be thought of like this. It can be a This can be the first iteration, it can be the second iteration. So this can be put below the patch, and V0 iterations for circular polarized response also can be tried out. This is very important design aspect which is there for realizing a fractal shape geometries, defected fractal shape geometries for circular polarized response. Okay. Okay. So this is about the fractal shape geometries. So here we complete your defected ground plane structures antenna designs. What we have covered, we have understood the requirement of why the defects are created on the ground plane. We have understood how the cross-polar level reduction is obtained by creating the defects on the ground plane. We have understood how the compactness is obtained by creating the defects on the ground plane, its comparative measure with respect to the slot on the patch. Then wideband designs, the possible options for research in the wideband design. So many configurations in fact are there. Lot of literature is there. One can analyze and come up with their own original explanation or design methodology. And then we have studied a fractal geometry. Similar study can be applied to other fractal, because triangular fractals can be drawn, V-slot fractals can be drawn. So similar study can be done. They can be analyzed with a coaxial feeding. They can be analyzed with a proximity feeding, because when you analyze with a proximity feeding, you can increase the substrate thickness. So when you increase the substrate thickness, axial ratio bandwidth, reflection coefficient bandwidth, that is the S11 bandwidth, can be increased. So all these possible variations are there. Remember, in whatever lectures I have covered, I have tried to concise and put the information for the users or the readers, but lot of literature is available in the open book or even journals where new things are coming every day. So we need to read, we need to understand, and then we need to explore different configurations. So keep looking at different configurations from different journals every day related to all the areas of microstrip antennas. So that will give you lot of different new thoughts, lot of new initiative thoughts can be developed for realizing different configurations. So that is about the defected ground plane structures. The last topic which remains is the antenna measurements. We do have separate videos related to the gain measurement, related to the radiation pattern measurement. You can refer those videos, and even we do have videos related to the bandwidth and S11 bandwidth impedance measurement, where using VNA we have actually shown the procedure to measure the impedance bandwidth or S11 bandwidth of the antenna. Similarly, we have shown we do have videos related to the pattern measurement, E-plane, H-plane identification, as well as the gain measurement, 3 antenna measurement method, which students do implement during the radiating system course in the semester 6. So here we conclude the defected ground plane structures antenna. Do refer our videos related to the antenna measurements which are there separately. Thank you.